Hey everybody. I wanted to show you a problem that I worked on with a student. Sadly, that recording didn't get saved, but I'm going to try to reenact it here if we can. So there was a couple of different questions that we explored. Here's the first one. So we're going to start off with negative r is equal to negative 27. Now, I like to think of this as a story because in my math classes, in my math on my work, I don't work for the math. The math works for me. The formulas work for me. The equations work for me. It's my thoughts, my logic on the paper. So there are no rules that I'm trying to follow. I'm just checking at every single moment that I'm changing the appearance of an equation because we're starting with something that we're told is true. So I can change its appearance without changing that it's still true. I just need to make sure I don't change the meaning. So that's going to be the common theme. We're going to change the appearance without changing the meaning. This right here, if I look at negative r, I know that negative means opposite. So I can think of that as the opposite of r. So the opposite of r equals, and then on the right-hand side, I have negative 27. That's the opposite of 27. So I have the opposite of 27. Now, if I just thought of that without any rules, symbols, need to haves, or math teachings, if I just said the opposite of r is the opposite of 27, it sounds a lot like r has to be the 27. And that's exactly where the answer lies. R is equal to 27 because we have the opposite of r has to be the opposite of 27. So it's like I'm undoing those opposites. How can I undo the opposites? Well, I know that the opposite of an opposite is as if nothing happened at all. And I'm kind of thinking to like the cha-cha slide, right? Like wedding dancing, we've got reverse, reverse, where people should turn around and then turn back. It's like we've done nothing at all. Or if I decide that I'm going to undo something and redo something, it's like I've done nothing at all. So one way I can think of trying to undo these opposites is I could try to opposite the opposite. So we could look at this as the opposite of r. And that's a way that I can show my work on the paper. It's like the opposite of 27. And I know logically from me that opposite of opposite undoes something. So opposite of opposite is if I have done nothing at all and I'm left with my r, and the opposite of 27 is as if I've done nothing at all and I'm left with my 27. Now, how do we show this on the paper? How does a traditional math class look? Well, we can think of this as being the opposite of r equals the opposite of 27. That's where we started from. And making things opposite is by making them negative. So I could make this a negative on the left-hand side. I'll make it grouped so I don't lose track of what's what. And I can make it the negative of what I have on the right-hand side. So I'll group it and make it negative. So in the negative, negative r, negative and negative makes positive. It's like I'm doing and undoing. And on the right-hand side, I have negative, negative 27 makes it a positive 27, like I'm doing and undoing. So this is what we're doing in our work every time we try to make things opposite. We're considering doing and undoing, because this line of work right here, where I wrote it with opposites, is exactly what this means. The opposite of an opposite of r is the opposite of 27. So again, none of this is rules. It's all logic. It's all what should make sense to us. And if it doesn't make sense, then we explore it further. Okay, so that's a great one. Let's now take a look at another problem. Let's go ahead and section off and consider something with fractions. Maybe something with t minus 3 over 2 equals 10. So again, we're not going to approach this with rules. We're going to approach this with logic, right? Because we know that we have the ability to do and to undo. So let's look at this problem. If I asked, what is bothering you about this problem? That's a good place to start, because what's bothering you, we can always undo, right? That's part of the beauty of math. The beauty of logic is we could just consider what it would be if we undid it. So here, if I ask, what is bothering you? What I get from students a lot is that the division by 2 is bothering us. And I think that that's a really good place for us to start. Because if I look at t, if t is the goal here, after all, to find what this mystery number is, I have t minus 3, which is sort of like one chapter in this story. And then I'm taking that entire t minus 3 number and dividing it by 2. So if I want to kind of undo this story and go backwards layer by layer, we're not going to start with undoing the 3. The 3 is trapped within the division. We'll start with the 2. The 2 is both the outer layer of this kind of metaphorical onion, as well as a thing that is bothering us. So how do we undo this 2? Well, the 2 is happening through division. That's what this bar means. So I can do the opposite of division as a way of undoing it. The opposite of division would be multiplication. So let's try multiplying both sides by 2. We multiply the left-hand side by 2 because we're trying to undo, and we multiply the right-hand side by 2 because we're going to keep it balanced, change the appearance without changing the meaning. So on the left-hand side, let's hold our motivation. 2 was being multiplied so that it would undo the division. So let's undo the division, and we should be left with t minus 3. On the right-hand side, we can simplify. That just makes this look easier. 2 times 10 is 2 times of 10. 10 and 10 makes 20. So 10 times 2 is 20. We can then ask again, what is bothering us? We want t to be alone, so the minus 3 is bothering us. And I can ask again, how do we get rid of it? Well, we could get rid of it by adding 3 to both sides. So I could add 3. Let's add 3 and add 3 to keep it balanced. That's going to be 3 plus t minus 3. Well, that's the same thing as t, where I'm adding 3 to it and taking 3 away from it. That sounds quite redundant. Adding 3 and then taking away 3 is really just a large way of saying nothing's happened. It's doing and undoing. It's a waste of time, right? Undoing and undoing hasn't done anything at all. So we might as well just not do it. We'll take that away. We're left with t on the left-hand side. And on the right-hand side, I have 20 and 3 makes 23. We can make that our final answer then. T, this mystery number, is 23. And it's always helpful to go back and double check it in our original story. Remember that our original story was t minus 3 over 2 is equal to 10. We can check that with 23, plug it in. 23 is t, so I can replace things with things that look different and mean the same. Again, changing the appearance without changing the meaning. So 23 minus 3 over 2 equals 10 has the same meaning as t minus 3 over 2 equals 10. And I can simplify the top. 23 minus 3 is 20. So I have 20 divided by 2 is equal to 10, and I think that looks really, really good because 20 divided by 2 is 10, and 10 is most definitely the same thing as 10. So if this is true, and it is the same meaning, just different appearance all the way up, so this has to be the same meaning, this has to be the same meaning, this has to be the same meaning, then I have said this is true. So 23 equals t is true. So our original equation is true. Everything is true, and we have good truth. Excellent. Now, I want to stress that none of this is the correct way. There is no such thing as the correct math. There's just math that makes sense and math that's changed the meaning accidentally. We need to fix it so that the meaning stays the same. It's just the appearance that is shifting. So this is one way of solving these problems, but to compare and to show you that there are multiple ways of solving these problems, I just want to grab an example. Let's go ahead and shrink this over. We'll move it off to the side. Let's do a problem like this. Let's do t minus 5 over 2 is equal to t minus 4 over 3. Now, again, notice that I'm going to try to keep the questions very consistent because it should be the same trigger every single time. And it's just, how do we handle the problem? It's treating math like a problem-solving activity, which is really what it should be all the time. So if I'm looking at this problem, I might ask, what is bothering me? Right? That's the question I always ask. What's bothering me? And then how do I undo it? There's a lot of things that can be bothersome here. One thing that looks bothersome if I just read left to right is that, again, there is a 2 on the bottom of this fraction. I'd like this division by 2 to go away. We have a strategy for that. We can multiply both sides by 2. Let's multiply both sides by 2. In doing so, on the left-hand side, I would be left with, well, the 2's cancel away. That's the reason I did this to begin with. And that would be t minus 5. On the right-hand side, we have a few different options. We could multiply 2 to both the parts of the numerator, because that's where multiplication goes, right? Multiplication is many pieces. The number of pieces is on the top, which is why like 2/3 is two number pieces of things that are a size 1/3. So we can multiply this on in. I'm actually going to hold off on that for just a moment, because I see something else I want to do instead. Before I multiply that in, I find it annoying that there is a fraction on the right-hand side. Do we see the t minus 4 divided by 3? That looks bothersome to me. I would like it to be t minus 4 divided by 3, and I'd like to undo that. Let's do it by timesing by 3. So I can multiply this thing by 3. Now, just to kind of show that we want to be careful about just placing times 3 anywhere, I'm going to put it just on the right-hand side where we might have naturally put it. And over here, I'm going to multiply the entire side by 3. Thankfully, we know from our commutative property that it doesn't matter what order I do my multiplication. So what I can do to make this nice and explicit in my work is I can switch the order of this multiplication using that commutative property. And again, the commutative property is not a rule. It's a truth that has to be, as I explained in one of my other videos where I talk about the commutative property. You can look that up on the YouTube channel if you'd like. All right, so I'm going to go ahead and on the left-hand side, what do we want to do? Well, this looks like easier distribution, so I might choose to distribute here. I can multiply both things by 3. That would be 3t minus 15. On the right-hand side, I have t minus 4 divided by 3 and then times 3. Well, that sounds redundant. Divided by 3 and times 3 is redundant. So I can do t minus 4. And I still have my multiply by 2. 3t minus 15. Well, now I have nice, easy distribution on the right-hand side, because this is 2 times of t minus 4. That's 2 times of t and 2 times of minus 4. A minus 4 and then minus 4 more makes minus 8. So that must be 2t minus 8. And on the left-hand side, I have 3t minus 15. So we ask again, what is bothering us? Perhaps the thing that's bothering us is that t is appearing in 2 different locations. I have a location of it here, and I have a location of it here. Well, if I want to get rid of one of the locations, maybe I'll choose to get rid of the 2t location. I'll get rid of the 2t location by taking it away. And I'm going to take it away on the other side to keep this all balanced. 3t minus 2t gives me positive t. I still have my negative 15. And on the right-hand side, 2t take away 2t is as if I had nothing at all. So I'll remove that and be left with the negative 8. And now I can ask, what else is bothering me? The t not being alone looks bothersome, so I could try to get rid of the negative 15. The opposite of that would be positive 15. I'll add 15 to both sides. And we have t is equal to negative 8 plus 15. On the number line would be starting at negative 8 and then going 15 up from there, which I think would land us all the way over to positive 7. And that's going to be a nice final answer. Again, let's double check that. So that's going to be 7 minus 5 over 2 was the original left-hand side. And on the right-hand side, it was 7 minus 4 over 3. 7 minus 5 is 2. So we have 2 over 2 is 2 over 2 is equal to, on the right-hand side, 3 over 3. And I know 2 divided by 2 is 1 and 3 divided by 3 is 1. So if this is true and it's just a different appearance of this one, this must be true as well. And t equals 7 is a good answer. Now I'm going to keep this up for a moment because I'd like to show you that there are many things we could have chosen to do, none of which are wrong. One thing we could have chosen to do is perhaps we could have looked at this division as saying both things were being divided by this 2. Right? So I'm going to write a separate copy of this problem. T minus 5 divided by 2 equals t minus 4 divided by 3. Again, let that be a story. There's a story here. T minus 5 is being divided by 2. That means t is being divided by 2 and the minus 5 is being divided by 2. So that I can write that as t is being divided by 2 and the minus 5 is being divided by 2. On the right-hand side, t is being divided by 3 and the negative 4 is being divided by 3. So we can make this look like fractions. Now, maybe we like this, maybe we don't. At this point, Usually people say, I don't like the fractions. And I say, great, then let's get rid of them the same way that we would have over here. We could multiply everything that has a divided by 2, which is the whole left side. And we'll do it to the right side to keep it balanced. That's going to start to make this problem look a lot like this problem. But here's an even more creative solution. If we both like to get rid of the 2's on the denominator and the 3's on the denominator, we could choose to multiply by 6. If we multiply both sides by 6, check this out. 6 is going to divide or multiply in here. So we have 6t divided by 2. It's going to multiply into here. So we have minus 6 times 5 would be 30, 30 halves. And then we have on the right-hand side, 6 multiplying on in, 6t's divided by 3. And 6 times 4 would be 24. So negative 24 thirds. Well, the nice thing about multiplying by 6 is that it gets rid of both the 2's and the 3's. Because take a look at this. 6 divided by 2 is 3t. 30 divided by 2 is 15. 6 divided by 3 is 2 with the t. And 24 divided by 3 will be 8. So we have a minus 8. It's really nice to see that all of these fractions can go away if we are multiplying by something that is the common multiple of both 2 and 3, because it would get rid of what would have been the common denominator for 2 and 3 if we had tried to work these together like fractions. And again, we get very, very creative methods. This looks just like this, so we skipped a lot of work with recognizing this creative method. And there's even more methods on top of this. We could have done a combining with common denominators. We could have been trying to group t's to one side and factor. There's so many different options we have. So remember, the math is not controlling you. You are controlling the math. The math works for you. So we only do things on the paper that change the appearance and don't change the meaning. But most importantly, we only do things on the paper that we understand and can explain.